Hi, we are Group 1. This is the presentation for the Network Embedded System, and we are going to talk about network architecture for in-vehicle network. As we all know, the demand of the vehicles are increasing dramatically in Europe. Virtually all cars on the market today use wired communications, such as CAN bus, LIN bus, and FlexRay. With the recent development of wireless technology, compared to wired communication, wireless communication can become a viable alternative because it is easier to install, repair, and has greatly increased flexibility. What is the in-vehicle network? In our project, it is the wireless communication for inside cars. We can use it to control the doors, the seats, or something else. In order to determine if wireless in-vehicle network can be a viable alternative to wired networks, investigating was done to find what the properties and design criteria are for wired protocols. Based on the information and the given knowledge of wireless protocols, a design was made where criteria like reliability, flexibility, and ease of use were taken into account. The choice was made to use a tree topology in combination with the industrial time-slotted channel hopping protocol. To validate if the properties of the wireless network are comparable with the properties of wired networks, a simulation was done in Koja.
If we chose wireless communication, because wireless communication are not reliable like wired communication, so it won't be applied for critical parts inside the car, like airbag, speed meter, steering, front or back lights. The sensors of wireless communication are used for airflow sensor, battery indicator, or parking sensors. The actuators are used for seat heating, windows, or interior lights.
As you can see from the graph, there are 4 layers. They are MAC layer, network layer, RDC layer, and radio layer. Then we have to choose network protocol. For topology, we chose tree topology. For MAC layer, time-slotted channel hopping is chosen, and we used IEEE 802.15.4. The IEEE physical and MAC layer characteristics are used for establishing connectivity between devices with low power consumption, low cost, and low data rate. Because of these properties and the fact that typical radio range is 10 meters, it was decided to use this wireless standard. The frequency bands are 2.4 GHz and 868 MHz in Europe. Maximum package size is 128 bytes with payload of 104 bytes. 64-bit IEEE or 16-bit address can be used. The MAC behavior mode time-slotted channel hopping was selected. This channel access method is designed for industrial automation, process control, and equipment monitoring. It supports multi-channel and multi-hop communications and uses a slotted medium access on several channels. It reduces the effect of interference and it improves the reliability of low-power wireless communications by means of guaranteed access.
As for the network protocol, there are several topologies that we can use for our project. For example, the point-to-point topology, star topology, mesh topology, hybrid topology, and tree topology. Finally, the tree topology was chosen for the in-vehicle network of the car. The main reason for choosing this topology is because the message should be able to hop to the source node. So that's why we exclude the star topology. And the number of links that can be used should be minimal. So we exclude the mesh topology. Then, because of the relative consistent number of the sensors and the low transmission range, there were not that high requirements in our project on the scalability and the self-organization of the network. Next, let's talk about the tools to do our simulation. We used Koja to build the architecture for the in-vehicle network and to do the simulation. As you can see in the slides, there are 3 advantages of using Koja. It's free, it provides lots of type of nodes, and it can simulate a big network. Alright, Contiki is an operation system designed especially for networked memory-constrained systems with a focus on wireless sensors. Although a new version of Contiki NG is available, but we still choose the last Contiki 3.6 because the NG version is still under development. Contiki supports a wide range of protocols over the OSI model. Koja, on the other hand, is a simulator contained inside the Contiki system, which allows emulating for networks of sensor nodes while offering some tools to monitor and look deeper into the network in a Wireshark style. That's why we choose Koja to simulate in our project.
For setup step, Koja also offers many types of modes to choose from. Those modes mimics the real hardware. In the beginning, we picked the simple sky mode. However, the teeny memory on the later mode was not big enough to fit the code size. Therefore, we switched to Z1 mode. To distribute the nodes in the vehicle, we took into account the distance and the fact that there are usually more sensors at the front side of the car than the rear side. In total, we distribute 14 sensors in the way shown in figure, with node 1 being the coordinator.
As of challenges, we faced a problem while trying to use IPv6 on Koja. After some research, the problem was located to be the installed MSP430 GCC compiler. It had a bug in the buffer size, and the problem was solved by upgrading the MSP430 compiler to a more recent version.
Next, we did the simulation part. For latency, it is the average of the difference between transmission and reception.
As for the results, finally, we measured the latency and the parameters of reliability. The results of the wireless sensor network were taken from the log.txt files that were generated by Contiki. Based on the difference for initialization of a process and the ending of a process, it was possible to determine what the times was for transmitting, idling, and initialization. We showed these three graphs in the slides. Furthermore, the mean and the maximum latency were determined based on the time it took for a message to be sent from one node and to be interpreted by the receiving node. The mean latency was 27.1 ticks, which is 867.2 microseconds, and the maximum latency was 46.4 ticks, which is 1484.8 microseconds.
In conclusion, wireless network could be a real alternative to wire for some applications in vehicle. As explained previously, wireless sensor network can't be used for vital applications in vehicles, but according to our results, wireless sensor network could be a viable alternative to Limbus in future vehicles, with the base station of the tree topology connect to CAN bus or FlexRay to relay it to the rest of the car. Moreover, wireless sensor network seems to be a good solution to design sensor network in heavyweight vehicles. To go further, we could try to implement more nodes in the simulation to see if the latency of the network remain the same. Therefore, in the simulation, we don't take into account of the security of the wireless network, neither of the collisions of sensor nodes from other cars, which could be close to the wireless sensor network. Also, maybe we have to take into account the possible reflection of signal inside the car. That's all. Thanks for watching.